All right. Good morning, everyone. Recording is now started. So you may have noticed that we are a little bit behind our lecture schedule. We're 2 days behind, but we'll make some good strides to catch up. The section on lines and planes took a little bit longer than I allowed for in the schedule, and sometimes that's typical. But we'll be getting into the calculus part now, and so this is where we can sort of pick up some lost time, which is not a problem. So let's get into today's section. Actually, we're going to be trying to get through the next two sections today. So 13.1 is actually a fairly short section. We've already done half of it. And then section 13.2 is the calculus part of this section. So we're on vector functions and space curves. So just to remind ourselves where we're at or what these were, we are basically building off of what we did in calculus 1 with parametric curves. So we have a parametric curve C. In this case, we are looking at it in space. In calculus 1, we just looked at it in the plane. But in space, it's given by a triple of functions, f, g, and h, where each one of them is a function that tells us what the x, y, or z coordinate of a point is at a given time t. We're going to think of t as a time parameter. It sort of helps when we think about how these curves are parameterized. You don't have to, it doesn't have to be time, but it's a nice way to think about it. So as time changes, the point of a particle changes as it moves around space, and its location is given by these three functions, each controlling the one corresponding component. So we can take this parameterization, which really consists of three equations and three functions, one equation for each function, and we can stick it all together into just one vector equation. And that's what we've done down here. We said, let's just form a vector with those three component functions. And rather than call them f, g, and h, I've just referred to them as functions h, y, and z, just to emphasize that it's a function controlling the x coordinate, another function controlling the y coordinate, and another function controlling the z coordinate. And so our example that we did was we had this vector function r, whose x component was given by cos of t, whose y component was sine of t, and whose z component was t. And we said that this defines what we call a helix. It's sort of this spiraling shape that happens when you let the variable t change. And I just wanted to point out that if we go to math3d.org and we go add an object, these are what we're talking about now, parameterized curves for the next couple of sections. So if you click that to add that kind of an object, it comes up, parameterized curves. I'll just get rid of the surface in the background. And this is the prototypical example of a parameterized curve in this software. It's cos of t, sine of t, t, and that was that spiral shape we get. If you wanted to make it a little bit wider, maybe I'll make it 2 times cos of t, so the x coordinate is 2 times cosine of t for any given t. You can see it sort of stretched it along the x axis. If I want to shrink along the y, maybe multiply by 1/2, then I can kind of get this spiraling shape where we can just control the individual components, the x component, the y component, and the z component. So that's a parameterized curve, and that's how we can very quickly sketch them. We can just plot the three functions into these components. All right. Now we're into the new stuff for today. So these are called vector valued functions because whenever we take a value of our parameter t, what it associates is this vector r of t. So we've got a real number coming in for t and a vector coming out. So when we talk about a function and the kind of output it produces, we call that the value of the function. So this function r is producing a vector as an output. So we call that a vector valued function. The limit of a vector valued function is shown here. It's how we can compute it. So the limit of r of t as t goes to some value a, we just get it by computing the limit of each of each individual component. So the limit, what is the vector r of t doing as t goes to a? It's wherever the first function f of t was going, comma, wherever the second function g of t was going as t goes to a, and so on for the third component. So it's just the limit of the individual component functions. So that makes limits quite straightforward in the sense that a limit of a vector valued function is just 3 limits that we would have done in calculus 1. We say
Sorry,
that.
quick question.
Yeah, go for it.
Why do we need? Why would we take the limit of a vector?
Why would we take
A valued vector?
Exactly. Yeah. Why would we take it? Because actually it's not in this section, it's the next section. The derivative. The derivative is defined by a limit. And so we need to know something about limits in order to work with derivatives. So that's just a very quick answer to your question. If we want to do things with derivatives, we need to know limits. The other reason we'd do something like this is, let's say I had a vector valued function and I wanted to know what happens. Maybe it was defined, there's maybe I should do it this way. Something like this. It was maybe piecewise defined. So the r of t was defined to be, I should change these because I want this one to be the whole and this one to be the solid. So we've got a hole in our graph, but it's filled in somewhere else. And so if you think about this, it's sort of like our particles moving along, and then at an instant in time, it's sort of beamed to another location. And then after that instant in time has passed, it's sort of beamed back to our current location, continues on. And we'd like to know, what is the value of this hole here? That would be computed by taking a limit as t goes to a. So this would be our r of a value, and this would be the hole occurring where t is equal to a. So it's the same kind of things that we would have for calculus 1. We're now just going along curves that can double back on themselves, just travel around in space. So we've got a much more general type of curve we're looking at here, and we can still talk about limits of those. The most important way we're going to use limits, though, is in the derivative. The other thing we can use limits for is to talk about whether a space curve is continuous or not. And that's sort of like the example I drew up there in orange. That would not be a continuous curve because you can't essentially trace along it without lifting your pencil at that t equals a value to draw the point somewhere else to then come back and finish drawing the curve. This idea of lifting your pencil is captured formally with this notion of a limit. So we say r is continuous at a point a if the limiting value of the function is equal to the value of the function at the point. All right, let's do an example. Find the vector equation and parametric equation for the line segment that joins these 2 points. So I've got a point P, 1, negative 1, 2. I've got a point Q, 4, 1, 7. And we'd like to find a parametrization for the line segment that connects them. So we don't want the line. So this is the subtlety here. It's the line segment. So we don't want the line that goes through those 2 points because that line would be infinitely long in either direction. It would just go off forever in either direction. We want the line segment that joins these 2 points. So I just want the segment of the line that has these 2 points as its endpoint. And we'd like to come up with a vector equation for that. So the idea is we can proceed just as we've done before. We'll find the vector that goes from one to the other. Let's say that that's vector v. So vector v is going to be the vector that points in the direction of the line segment. We can get it as tip minus tail. So it's the vector, maybe I'll say it's the vector from P to Q. And so it would be tip minus tail. 4 minus 1 is 3. 1 minus 1 is 2. 7 minus 2 is 5. And now the line that we're constructing, I'll call it L with a vector symbol on top. Instead of R, we can use other variable names. So I'll call it L just to signify that this curve is actually a line segment. And so how do we construct this? Well, I'll write down the equation of the line first The line would be the point that we know on it, at least the position vector for that point that we know on it, plus a multiple, so a scalar multiple, which we'll call t, of the vector that points in its direction. So this would be 1 minus 1, 2, plus t times 3, 2, 5, or we could write it as 1 plus 3t, negative 1 plus 2t, and 2 plus 5t. So there is our vector equation of the line. Vector equation of line. But we want the line segment. So what do we do in order to get the line segment? So I see the comment there. There was a message asking, can I explain the term vector valued function? So it's a function whose value is a vector. So we just sort of interpret it backwards. A vector valued function is a function whose values coming out of them are vectors. So line segment, yeah, we restrict the value of t. You got it. So that t is saying start at point P and take all possible multiples of v in either direction. That gives us the entire line. But we don't want the entire line. We want only the segment. So basically I want, a little multiple. So added to point P, I want a little multiple of v, and then slightly longer, and then slightly longer, and slightly longer, until I get out to P plus which multiple of v is going to get me out to Q. What multiple of v is going to be the biggest multiple I'm going to use in order to get out to Q. So what value of t? Like t being 0 is going to keep me at point P. If I take t to be a half, then I'm going to be halfway to point Q. So what do I want for t? 1 plus 3t, negative 1 plus 2t, 2 plus 5t, where t ranges between what and what? Yeah, the biggest value is going to be 1, smallest value is going to be 0. And so that's the line segment. We just had to restrict what values of t we wanted. We're only going to take the multiples of v that are between 0 and 1. If we took multiples that were bigger than 1, then we're now on the other side of the point Q. So we're off of the line segment and more onto the line that the ray, what we call a ray, half infinite line segment, or sorry, a half infinite line that goes from P through Q and then off to infinity, essentially. That's if we take t to be bigger than 1, we'll get those points further over than Q. If we took t to be negative, we'd get points on the other side of P. So we wanted to restrict to just 0 to 1 to get the segment. So that's the vector equation. And then we can also get the parametric equations for the segment. So parametric equation for the line segment. And those again are just unpacking. 1 plus 3t, y of t is equal to negative 1 plus 2t, and z of t is 2 plus 5t, where again t is restricted to be between 0 and 1. So those are the parametric equations, and the one above is the vector equation, because it's a vector valued function that's describing the curve. Single value going in, vector coming out.
Sorry, can you repeat one more time why we chose 1 specifically? We said that we chose 0 as the lower limit, so to speak, because we set it as point P. But why specifically 1?
So it's all boils down to this vector v that we're using for the direction vector of the line. So in our diagram, that's our vector v here. So the idea is when we take t to be 0, we are right at this point P. And then if I look at taking t to be a half, let's say, in our line segment equation down below, in the orange one down below, what's t of a half? Well, we're starting at the point P, and then we're moving along half of v. So that would be right out here. this would correspond to t equals a half, because I've only gone halfway along the vector v. And that means, you know, if I keep going, how do I get to point Q? Well, I have to start at point P, and I have to go the full length of the vector v. So that means I have to take a scalar multiple of 1 of the vector v in order to get out to Q.
That makes sense. Thank you.
You're welcome. All right. Let's do the last example in this section. This says find a vector valued function, or find a vector function that represents the curve of intersection of the paraboloid and the parabolic cylinder. We haven't really talked about these terms paraboloid and parabolic cylinder. The idea is the set of all points of these equations define some surface in space. And the surface just has these names. One of them is called a paraboloid, the other is a parabolic cylinder. We will come back to 12.6 where we talk about this points of terminology, but we don't need to know that in order to answer this question. It just wants to know, what is the set of all points that lives or that satisfies the first equation, z equals 4x squared plus y squared, and also satisfy the second equation, y is equal to x squared. So what is the set of all points that satisfies both of these equations? So what we want to do is we just want to start this by saying, well, let x, y, z be a point that satisfies both z is equal to 4x squared plus y squared and y is equal to x squared. So at some point, whatever the values are, that satisfies both of these equations. That's what it means to be on the intersection of them. It has to satisfy these two equations. The nice thing about this is we can combine these two equations together. We do kind of what we do in linear algebra. If these were linear equations, we could substitute for one of the variables in the other equation. So in this case, I have y is equal to x squared. So I could take that and I could plug it into the first equation, and I get a 4x squared plus an x to the fourth. So I'm plugging in y equals x squared into first equation. And now, what does this tell us? This tells us that the point is in the intersection if we have that the point is of the form x. What would the y value have to be? Well, this equation tells us that the y would have to be the x coordinate squared. So we got y would have to be x squared. And what would the z value have to be? Well, this equation tells us that the z value would have to be 4x squared plus x to the fourth. So this would be 4x squared plus x to the fourth. And so that tells us that any point on the intersection has to be of the form x squared, 4x squared plus x to the fourth. So what we have is, therefore, for t in R, the curve, maybe I should say it this way, the point t squared, 4t squared plus t to the fourth. So all I did was just replace x with the variable t, because x was essentially a dummy variable in that first equation. It was just whatever the x value is, the y value better be the square of it, and the z value better be 4x squared plus x to the fourth. And if those conditions are satisfied, then it's on the intersection. So therefore, for any t, this point is in the intersection. And now we have, therefore, the curve of intersection is r of t. We can now write it as a vector equation or parameterized curve, t squared, 4t squared plus t to the fourth. And so there is our vector equation. And t can be anything from negative infinity to infinity. There was no conditions on what t was. So we did exactly what we would have done in linear algebra, but we did it with nonlinear equations. And that was the idea here. We can take these techniques that we learn in other courses and we can certainly apply them in new situations. So I'm going to give you a feel for what we've just done here. So I will try to drag this up a little bit so you can still see what's in the background while we're constructing. So what I'm going to do is I'm going to, as I said, we haven't really talked about those surfaces yet, but we can go ahead and plot them anyway. I'm going to plot an explicit surface. This is just what is z equal to, and our first equation is z is equal to 4 times x squared plus y squared. So that's that first surface, whatever it is. It's called a paraboloid, but we'll get to that in 12.6. Then I'm going to add another object, y equals x squared. I'm going to have to make that an implicit surface because it's not z is equal to something. It's one of the other variables, y is equal to something. So I need what's called an implicit surface where I don't have to worry about solving for z specifically. So we got y is equal to x squared. I'm just going to change the color to green so we can see it a little bit easier. And we can see its intersection. Maybe I'll make this one a little bit higher. So I'll let the z value go up to, I don't know, 15. So it just really goes up high. Now we can start to see the intersection. Drag this down a bit. There'll be these points that live on both of these surfaces. So wherever the green and the blue surface intersect each other, those are the points we're interested in. And what we've done, I'm going to plot the parameterized curve we found now. The parameterized curve we found was t squared and 4t squared. I'm going to make sure I put a multiplication sign between it because sometimes it interprets this as multiplication, sometimes it doesn't. So just to be sure, we'll put it in there. So 4t squared plus t to the fourth, that's our curve. I'm going to change it to a different color, maybe yellow, and I'm going to increase its width. Maybe I'll make it 12 just so we can see it. Nice big width. And I'm going to do one more thing. I'm going to increase its z bias so that whenever there's two objects occupying the same point in space, show me this one over top of the other one so that the yellow will bleed through. And we can see that that's exactly what we found here. That's the curve of intersection, and we found it as a parameterized curve. So that's what we've done in this example. We've extended those ideas from linear algebra where we know how to find the intersections of two planes. We could solve it as a linear system, find the line. We've now got the ability to solve for the intersection of two more general type objects, surfaces, which aren't necessarily given by linear equations. And this is where parameterized curves can come up and help us in those situations as well. All right. There's a question in the chat that says, why do we need a t? Because isn't the vector from p to q? So let's go back to this one. There was a question about why do we need the t? The reason we need the t, and I'll just point out where it is. So the t is right here. The reason we need that t, or even this t, is because we're trying to capture all points along the line segment. So I need something that controls which point I am along the line segment. So imagine that I wanted to capture this point right here, that one. What is it? Well, to get to that point, I start at point P, and I have to move in the direction that V is pointing me in, but I don't want to go all the way to the end of V because that takes me to point Q. I want to move maybe a quarter of the way along. So I need to go, starting at P, I need to move a quarter of V along. And so that's what T is telling me? T is telling me how far along the direction of V have I gone. And I'd like to get all points between P and Q. So I have to let T be allowed to take on any value between 0 and 1 so that I get all points between P and Q. All right. Oh, you're welcome. So let's now, that's an introduction to vector valued functions or space curves. And this was an example of intersection. So a little bit more in depth about how we can use these sort of space curves. Now I want to get to the calculus of them, and that's our next section. So this is our next section, derivatives and integrals of vector functions. So a quick reminder, the limit of a vector valued function was just the limit of the corresponding components. So limit of f, limit of g, and limit of h. And that allows us to go and introduce a derivative. So the derivative of a vector valued function, put it in here in blue, is defined precisely how we would have defined the derivative in how we did define the derivative in calculus 1. You'll notice that there's a little prime here. So don't miss that there's a little prime there. So r prime of t, that's another notation that we're using. So dr dt or r prime of t both represent the derivative. And this is how it's defined. It's defined to be the limit of the difference quotient. So the function evaluated at t plus h minus the function evaluated at t divided by h. It just so happens in this case that our function has vector values instead of a single real number value, but we're using the same definition. What does this look like as a picture? Because that's really, you know, we write down the same definition as we did in calculus 1, and we just say, well, that's the derivative. But this really comes from a picture, something we want to capture. What do we want to capture? Well, much like in calculus 1, where the derivative was capturing the slope of a tangent line, we want this object, the derivative r prime of t, to capture something about the slope of the curve. Slope doesn't make sense when you talk about it in 3 dimensions. What would make better sense is just to say, what direction is the curve going in? And so that's what we're trying to capture here. If you're imagining you're flying along this space curve, maybe it's a roller coaster, and all of a sudden your seatbelt let loose, what direction are you going to be flying in? Because that's the direction that the curve was going precisely at that instant before it maybe turned and went around another corner. So maybe letting your seatbelt go is too graphic. Let's say you had your cell phone in your hand and you were taking a selfie or you're recording, and then all of a sudden you took this drastic turn and it slipped out of your hand. Which direction is your phone going to fly in? That's what the derivative is trying to capture. Which direction are you moving in right at that moment? So here's the corresponding picture that we'll sort of have in mind for this. I've got some origin and space somewhere just so we can have a reference position as well as reference directions. And then I want to know maybe right at this point. Well, maybe I shouldn't say right at that point just yet, but I'm interested in, what's going on? How is this curve sort of changing or moving as I move from that point to, let's say, this point? Well, what I can do is I can look at because this is a vector valued function, I can look at the vector value at t. So that's this orange vector here. We're assuming that this is our vector valued function, which we're going to call r. So at a given t, maybe we're at that orange point. And then a little bit later, at t plus h, we're over here. So that's r of t plus h. And so to capture which direction we were traveling in order to go from r of t to r of t plus h, so what direction were we, I'm at the orange point, what direction do I have to go in to get to the purple point? Well, the direction is just going to be the vector that connects the two. And that's r, the tip, r of t plus h, minus the tail, r of t. And I'm really interested in direction, not so much length. Length isn't the thing that I'm trying to capture here. I just want to know what direction did I have to go in to go from orange point to purple point. And so in order to get length, what I can do is I can scale it by something. I'll scale it by t. So depending on, maybe I should say, sorry, scale it by h. So I'm thinking of h as a small number. So if I divide it by h, this would be a longer vector. So that would be r of t plus h minus r of t, and we would divide it by h. So we're just scaling it. And that's in some sense going to give us a vector that we're really more interested in the direction, not so much the length. Now, once we've set up this difference quotient, then the question is, what's going on right at that orange point? So if I let
Sorry, can
h,
you explain
yeah, go ahead.
why you're dividing it by h?
Yeah, so here's the thing. If I now say what's going on right at that orange point, so I'm going to let h shrink to 0 because I want to know what's the direction I'm going in. So I let h shrink to 0. So I take a purple point that's even closer and even closer and even closer. So I'll zoom in. I'm taking these purple points, getting even closer and closer and closer. And those are giving me these green vectors. And notice that the green vectors are shrinking and shrinking and shrinking, and their value is going to 0 in length. I don't want to worry about length. I just want to worry about direction. So if I divide by h is a really small number. So when I divide by it, it's like scaling up the vector. So I'm still getting direction information. I'm just not losing the vector entirely. It's not shrinking to 0. And that's all what I want. I want to make sure that my vector doesn't shrink to 0. I just want to know what the direction is it's pointing in. I don't care about its length. So we take essentially a tip from Calculus 1 that says, hey, when you're interested in derivatives in Calculus 1, we wanted to find the slope, and it was sort of rise over run. That was the change in the y value over the change in the x value. So we were dividing by the change in x, which was h. And we're going to do the same thing here. We're going to divide by the change in the t value. So we're taking what is the change in the points, the point we're starting at, and the tip, and we're going to divide by the change in the time. And that's going to give us a vector that points in the direction that the curve is going in without having to worry about the vector shrinking to 0. Is r of t both the, so r of t is the generic gray curve for a specific value of t. We are looking at it as the orange point. So typically we would say, what's the derivative r prime of t? It says, well, pick a particular t value. Normally in Calculus 1, we'd say just pick an a value. What's the derivative at a? You'd say x is equal to a. We could have done that here, but we're trying to construct a function. So we'll keep the t to be just the same as the arbitrary variable. So for a given t value, plot the orange point, move a little bit away, plot the purple point, and now let that difference between them shrink to 0. And when we let that difference shrink to 0, what we get is, maybe I'll use a pink one. What I get is a vector like this. And that vector is our dr dt. That's the limit as h goes to 0 of that blue vector, the difference quotient. Okay, if it helps for you to think of a concrete example, just think of, let's say we were trying to find the velocity. What's velocity? It's change in position over change in time. So the change in position is the top, the difference between where you are and where you're going. That's your change in position. What's your change in time? How long you were traveling. And that's h, because you traveled from time t to times t plus h. So you've traveled h units of time. So you can think of this as, if it helps, think of this as change in position, and this as change in time. So then this would be velocity. So that might help in terms of a concrete example. So you're wondering why we're dividing by h? Well, that's the change in the input variable. Change in output divided by change in input, letting the input change go to 0. That gives us our derivative. That's just effectively what the derivative is in any situation when you're moving through calculus. It's always change in output divided by change in input. So the nice thing about this is because limits behave on components, the limit of, so our recall above here, the limit of a vector function is just the limit of its corresponding components. And the difference of two vectors is just the difference in their components. Then that tells us that the derivative of a vector function is just the derivative of its components. So let's do an example of this just to solidify that. Here I've got a vector valued function. R of t is cos 2t, t e to the t, and log t over t squared. We want to find r prime of t. What is r prime of t? It's just take the derivative of each of the components. Derivative of cosine is negative sine 2t times 2. That's the chain rule. The derivative of t e to the t is a product rule. Maybe I'll indicate that here, product rule. So it's the derivative of the first, which is 1 times e to the t, plus the first times the derivative of the second. And how about that last component? What's the derivative of log t over t squared? That one is going to be a quotient rule. So it's the derivative of the top, 1 over t, times the bottom, minus the top, ln of t, times the derivative of the bottom, 2t, all over the bottom squared, t to the 4th. And so there's our derivative. So the derivative of a vector valued function is the derivative of its individual components. And what this derivative is capturing at any given point r of t on the curve, this is the tangent vector at that point. So we'll get a picture of this when we do a more concrete example with some values. And we'll do that right after I've said tangent vector, but I should formally introduce what it is. So we call r prime of t a tangent vector to the curve C at the point R, provided that the derivative exists and is not non-zero there. The tangent line to the curve at the point is the line through P that's parallel to the tangent vector. So here's our picture that we want to have in mind when dealing with this. So I've got maybe some curve that looks like this. This is our curve given by r of t. We've got a point on the curve. That's our point P. And what we've done is we've now managed to construct the tangent vector at that point. So the tangent vector is r prime of t. And I'm going to move this word just down a little bit because I'm going to draw something above it. So that's our tangent vector at the given point P. So whatever P is, maybe P corresponded to the parameter T was equal to 1. So the tangent vector would be r prime of 1 there. Or P corresponded to the value of the parameter T equal to 3. Then the tangent vector would be r prime of 3. So we'll get to those specific calculational details in a second, but the idea is we can find the tangent vector there. It's given by the derivative. And the line that goes through that point P and is in the direction of the tangent vector is called the tangent line. What do we need to determine a tangent line? To determine a tangent line, we need a point on the line, which we got, that's P. And we need a vector that points in the direction of the line. That's what we've just learned how to compute, the tangent vector, which is the derivative. So now we can find tangent lines to space curves. They're related to the derivatives of the space curve vector function. The last thing we can do is we could strip off the length of the tangent vector by just dividing by its length. So r prime of t divided by r prime of t is known as the unit tangent vector. So that's the unit tangent vector, is to just strip off the length. So for example, if I made this vector have length 1, so length is 1, then this is called the unit tangent vector. And it's denoted by that capital T. Okay, so let's do an example. So this, I feel like, you know, we get sort of the big picture here, but sometimes the details are lost. It's like, how do I do this in a particular case? What is it that I actually have to do to find a tangent vector or tangent line? So let's go ahead and do this example. Find.
Sorry, can you scroll back up for like a second?
All right, are we good? Is it all right if I scroll down?
Yeah, thanks.
You're welcome. All right. So what can we do? So I've got this parametric equation for a line. So remember, this was our helix. So let's actually wipe out the previous construction, and I'll bring the helix back up. Actually, while I'm doing this, I will scroll back up. So just in case there are people still writing as well, because I can just work on this parameterization for now. So we're going to go parameterized curve just to get a picture. So here's our helix. And the question is asking for, just got to figure out where we are. We want to find the tangent line to the helix at the point -1, 0, pi. So I'm going to add a point. -1, 0, and pi. So there's our point on our helix. And we might want to think about which direction we are traveling on if this was a roller coaster. It's the direction of increasing t. Since t is controlling the height, it means that as t increases, we go up the helix. So it's like a ride where we're sort of traveling up the helix. We're going up the spiral staircase. If precisely at this moment we let go of our cell phone, which direction would it travel in? That's the bit that we're trying to figure out. Which direction would it go in? So is it going to go down? Is it going to go up? Is it going to go to the side? Which direction? So we need a vector to capture that direction. That's what we're going to do now. So let's get a feel for what direction it's going to go in. Okay. Well, the direction it's going to go in is going to be the direction that the tangent vector points in, which is given by the derivative. So we go r prime of t, and we can switch to our tuple notation. I don't have to use I hat, j hat, and k hat, though I'm going to use them interchangeably. Sometimes I'll use I hat, j hat, k hat as separators. Sometimes I'll just go right to our tuple notation where I use the angle brackets. So what's r prime? Well, I'm going to have to differentiate each of these. So a problem now, as you're observing in calculus 3, is usually multiple calculus 1 problems all done at the same time. So here's 3 derivatives we have to do, all to just find the derivative of a vector valued function. So a derivative of a vector valued function is equivalent to 3 calculus 1 problems. The derivative of cosine, that's negative sine of t. The derivative of sine, that's cos of t. And the derivative of t is 1. So that's our tangent vector at any value of the variable t. So whatever value t is, we plug it in here and we got the tangent vector at that point. We want to know the tangent vector at point P, which is -1, 0, pi. Well, in order to do that, we need to know what the value of the parameter is there. So the value of t is, what is the value of the parameter t that produces that point P on the curve? We got our helix there, little r of t for any value t, that gives us a point on the helix. what is the value of t that produces the point -1, 0 pi? Yeah, you got it. So t is pi. Why is that? So maybe I'll put y here. Why? Well, we're trying to set r of t equal to the point, -1, 0 pi. So I'll use the position vector. And r of t is cos t, sine t, and t. And the simplest one to compare is just the third component, because that tells me that t has to be pi. So that means if I go back to our construction, notice how I plotted my point by -1, 0 pi. I could have done that instead by taking the parametrized curve and sticking it here and using the value pi for each of these values of t, pi and pi. Get rid of that t there. And that's the same point, because when I plug pi in, cos of pi is -1, sine of pi is 0, and pi is the third value, or the third component, and so that's the point. So that was the first step, is to say, I've got a point. What was the value of the parameter that produces that point? Now that we have that, we can go back and we can say, what is our tangent line? Tangent vector and tangent line. So our tangent vector is r prime of pi, because pi is the value of the parameter we're interested in looking at. That's where the point is. This is the one that's controlling the specific place in space we're worried about. What is r prime of pi? That's negative sine pi, cos pi, and 1. So that's going to be sine pi is 0, cos pi is -1, and 1 is just 1. So that's our tangent vector. So that's our tangent vector. And now we want to find the line. So the line, maybe I already wrote line above, but we'll do it here. That's our tangent vector. And so now the tangent line is going to be, since r has already been used to denote the curve, I like to use a script L to denote the line. So what's our tangent line? It's going to be we need to know a point on it. We do. That's -1, 0 pi plus t times the tangent vector, 0, -1, 1. And so that's our tangent line. And I'm going to just move it down a bit and bring the construction in above so that we can see these things in action. Maybe something like that could be enough to see in the background. So we found that vector. Let's see what it means. I'm going to add a vector to my diagram. There, it's added a generic vector, 3, 2, 1. The one I want to add is 0, -1, and 1. So that's the vector that's pointing, or that's the tangent vector. When I look at my diagram, I can see that the vector, they've emanated it from the origin, and that's just because vectors don't have any fixed attachment in space. We can put them anywhere, start them at anywhere. They're only a direction and a magnitude. So what I'd like to do is I'd like to start it. Let's see if I can get tail. There it is. I'd like to start it at my point P, which is -1, 0 pi. And I'll minimize this. And there it is. I'll zoom in a little bit. That's what we just computed. That's the direction our cell phone's flying in if we let it go of it right at that moment on this roller coaster as we're going up here. If we let go of our cell phone, that's the direction it's going in until gravity takes over and then pulls it down. But that's a whole other question. So this is the direction the curve is moving in at that moment. Yep, there'll be practice problems for midterm 1. They'll come out by Tuesday. I'll get those all finished up by tomorrow. Okay, and now we need the line. So we can go ahead and say parameterized curve. There's the curve. Now we can go ahead and do the one we have below. That's -1, 0, pi is the point we're starting at, plus t times the direction vector. What's our direction vector? It is, there's too many brackets there. There we go. 0, -1, 1. And I need to make sure there's a multiplication sign between t and that. I'll change the color just so you can observe that what we've done is we've actually computed the tangent line there as well. So that's the tangent line. So why am I showing you these constructions? For two reasons. One is so we have a visual of what's going on and what the calculations are that we're doing. This is what they're the visuals. This is what we are doing using our calculus, our algebraic manipulations. These are the objects we're constructing. So now we can visualize them. The second one is when you're doing homework problems, that you don't need a back of the book. You don't need to check answers online in any form. You can just do the construction yourself and see, oh, yeah, okay, the vector I constructed, yep, that looks like the tangent vector, and the line, yep, everything looks good here. So I don't think I've made any mistakes. And so again, you've got the ability to check your work by doing these visualizations. That's what I wanted to get the emphasis with those first few assignments, is that you can check your work using these tools. All right. I just want to mention one more thing, and then we are essentially done with this section.
I have a question.
Can
So
you
the-
hold on for just 30 seconds, and
Yep,
then we'll
sure.
be at the end of the class. Perfect, thank you. So the differentiation that we just talked about, it satisfies all these differentiation rules. Basically, these are all the ones that we have for calculus 1. Derivative of sum is the sum of the derivatives. Derivative of a scalar times a function is a scalar times the derivative, and so on. We also get these extra ones as well. The derivative of a dot product is the dot product, is a product rule involving the dot product. So it's the derivative of the first dot the second plus the first dot of the derivative of the second. And same with the cross product. It's the derivative of the first cross the second plus the first cross the second. So these are just natural generalizations of the product rule, but now extended to vector functions. And then we also have a chain rule as well. So I will complete these last two examples in the video, and then next day we will get into 14.1. So I'll add an extra video on the end of this where I complete these examples, and then we're all up to speed for this week's homework assignment. All right, so that's it for today's class, and I'm just going to stop the recording.